A couple more examples of being able to solve these differentials of the first order by using substitution. This one's a little bit more rigorous than the other two. So we have this xy prime equals y plus root x squared plus y squared. So the first thing we're probably going to do is we're going to isolate the y prime term. So we're going to rewrite this, and we're going to have to do some algebra magic with this. So we're going to divide, and we're going to get y prime is going to be equal to y over x plus the square root of x squared plus y squared divided by x. Now we're going to use a trick where we're actually going to move the x under the radical. And we're going to rewrite this as y over x plus the square root of x squared plus y squared over x squared. Okay, so notice that all we did was we took the x that was on the outside and we moved it underneath the radical. And to do that, we had to multiply by the index of the radical, which was 2, since it's a square root. We're going to rewrite the radical, or the radicand in this case. So we have y over x plus the square root of x squared plus over x squared. So I'll just break this down. X squared over x squared plus y squared over x squared. Or finally, another way to write this is going to be y prime equals y over x plus the square root of 1 plus quantity y over x squared. Alright, now at this point I'm hoping it's pretty obvious as to what the substitution should be after we did this algebra. So let's define v to be equal to y over x, and I'm hoping you guys can see that in both of these there's a couple structures that contain y over x. We're going to solve for y by multiplying both sides by x, so y is going to be equal to vx. And then we're going to have to take the derivative of that using the product rule. All right, so we have a function of x, and then we just have x. So remember, v is a function of x, and then x obviously is a function of x. So when we use our product rule, this is going to become y is equal to the derivative of v, dv dx times x, and then the derivative of x is 1, so that's going to be v. And this is y prime. Right. So now we can substitute. So by substitution, y prime is going to become dv dx divided by x plus v. We said that y over x is v, and plus the square root of 1 plus v squared. I want you to notice now that this becomes a lot easier. The v's are going to cancel out. We get dv dx times x is going to be equal to the square root of 1 plus v squared. And now we just get one of these separable equations. And unfortunately, in this case, it's separable. And I'll show you why in a moment, why we say unfortunately. So we're going to rewrite this as dv over the square root of 1 plus v squared equals dx over x. And now we're going to integrate both sides. Now this one's easy. This is just ln of absolute x, and we'll just leave it as absolute x, and we'll say plus c. Unfortunately for this one, if that plus were a minus, then we could just say it's an arc sign. However, because it's a plus, and it's the radical of it, not 1 plus v squared, this one we have to use a trig substitution on. There's no way around it. All right, so to be able to do this one, we're going to have to let v be equal to the tangent of theta. All right, so unfortunately, it's just one of those ones where we have to use the technique. dv is going to be equal to sec square of theta, d theta. All right, so it's just like your regular substitution. Notice that tan of theta is v over 1, and we can build our triangle that way. So if we build our triangle, and you might remember from calculus 2, you need your triangle to back substitute. Remember, tangent is opposite over adjacent. And so the opposite is v, the adjacent is 1. And then by Pythagorean theorem, since a squared plus b squared is c squared, c is going to be equal to the square root of 1 plus v squared, right, in our Pythagorean identity. All right, so now we're going to substitute. So our integral now becomes, instead of dv, we have sec square theta d theta. And then instead of 1 plus v squared, we're going to have the square root of 1 plus tan square theta. Right. And this actually works out really nicely. We know that 1 plus tan square is sec square. And the square root of sec square is secant. So we're going to end up with sec square theta d theta over sec of theta. Obviously, we can cancel out one of the secants, so we're left with the integral of sec theta d theta. All right? And now we're going to look at that list of integrals. The list of integrals suggests that the antiderivative of secant is going to be the natural log of secant plus tangent. All right? So this is going to be equal to ln of the absolute value of sec theta plus tan theta. Right? And then also remember, earlier in the problem, that we took the antiderivative of the right-hand side and we got ln x plus c. Now remember, we have to back substitute for theta, all right? And secant, remember, is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. And then remember earlier, the tangent was just equal to v. Right? So remember, we have to back substitute. So now this is going to become the natural log. Hypotenuse is the square root of 1 plus v squared. Adjacent is 1. The tangent of theta is v. And then we have ln of x plus c. And then don't forget that we have to back substitute for v as well. Remember, v was equal to y over x all the way back up here. So v was equal to y over x, and we're going to back substitute. So one possible solution is going to be the square root of 1 plus y over x squared plus y over x equals natural log absolute x plus c. And if you wanted to, you could subtract ln from both sides. You could probably use that log rule where you could divide them both and clean up the answer a little bit that way. However, this is a pretty good answer implicitly as our general solution. All right, a second example of using that technique. All right, and this one's actually a little bit easier than the previous. So we have xy, y prime equals y squared plus x over 4x squared plus y squared. The algebra is a little more intensive, but the calculus is easier. As we did before, we're going to start by dividing by xy. So we get y squared over xy plus x square root 4x squared plus y squared divided by xy. X's are going to cancel, one of the y's is going to cancel, and so what we end up with is y prime is equal to y over x. And we're going to use that trick where we move the y underneath of the radical again. So it's going to be the square root of 4x squared plus y squared. And don't forget, when we move the y under the radical, we make that into y squared. Then we're going to divide these up, and we're going to rewrite this one last time algebraically. Y prime equals y over x plus the square root of 4 quantity x over y squared, because they're both squared, and then y over y squared over y squared becomes 1. All right, so that's as algebraically simplistic as we can write the differential. At this point, we're going to use a substitution, and it looks like there's two possible choices, because we do get a y over x, but then we also get an x over y. Right? And I'm going to show you how to take care of this. I always, from my experience, if you have to choose, almost always you're going to let v equal y over x, and I'll illustrate how that works in a moment. We're still going to get the exact same substitution as we did in the previous, so we know that vx equals y, and then we have to use a product rule. And our product rule says take the derivative of the first factor, so that's dv dx times x, plus the derivative of the second factor, derivative of x is 1, and that's going to be our y prime. I want you to notice that instead of using v, we could use the reciprocal of v. So 1 over v is going to be equal to x over y. And that's what we're going to substitute back in under the radical. All right, so let's go ahead and rewrite this. Remember, y prime is our dv dx times x plus v. On the right-hand side, y over x is v. And then we're going to add the square root of 4 times 1 over v squared plus 1. All right, and this is starting to look ugly, but we're going to use some algebra magic and clean it up. Canceling the v's, that's nice. dv dx is going to be equal to the square, or times x, excuse me, is going to be equal to the square root of 4 over v squared plus 1. All right. Now this looks like a pretty ugly sort of radical to work with, but in fact, it's actually not that bad. All right. We're going to have to do some algebra magic on this expression. Right? And what we're going to do is we're going to get a common denominator for the 1. Right? So we can rewrite 1 with the denominator of v squared. So we can rewrite 1 as v squared over v squared. And we can now rewrite the expression as the square root of 4 plus v squared over the common denominator of v squared. Another way to rewrite this, dv dx times x is going to be equal to the square root of 4 plus v squared divided by v, by taking the square root of that v squared. Right? Now, we can go ahead and separate. Okay, so this is a separable differential. So we're going to multiply both sides by the reciprocals to isolate. Okay, so I'm going to multiply both sides by v square divided by 4 plus root v squared. Or another way we could think of this is just take the reciprocal of both sides. In fact, that might be a little bit easier for everybody to see. And that's perfectly legal to take the reciprocal of both sides. So if I do so, because they're all, it's just one term on each side, so I would get dx over dvx, since dv and x are in the numerator, dx is in the denominator, v over root 4 plus v squared. So that's our reciprocal of both sides. We can now multiply both sides by dv, and now we have a really simplistic integral to try to evaluate on both sides. All right, we already know dx over x, ln absolute x plus c. And then the antiderivative of this expression, a little bit more rigorous than that because it's a u sub, but not a trig sub, although certainly we could make it a trig sub. Let's let u be equal to 4 plus v squared. The derivative is going to be 2v dv. We like v dv, but we don't like the 2, so let's divide both sides by 2 to get v dv. And so now we can rewrite the integral in terms of just u. So v dv becomes du over 2, and then 4 plus v squared becomes u under the radical. Right? So that's our substituted expression. Right? And now it's really easy. We still have this ln of x plus c. I'm going to factor out the 1/2, and I'm going to rewrite this radical as u to the minus 1/2. And we still have our du. ln absolute x plus c is going to be equal to 1/2 u to the positive 1/2 over 1/2. Remember that u was equal to 4 plus v squared. Excuse me. So we get ln of x plus c is equal to, the halves cancel out, the square root of 4 plus v squared. And then remember all the way at the beginning that v was equal to y over x. So our final answer, or one final answer, is going to be 4 plus the quantity of y over x squared. So hopefully, even though those two examples were a little bit more algebraically rigorous and also calculus with respect to integral rigorous, it shows you the benefit of using the substitution. So we'll do one more example in our third video of substitution, and then we'll move on to a specific type of substitution called a Bernoulli substitution.